In this lesson, we will focus on the reactivity series of metals with oxygen. Most metals form metal oxide when it is heated or burns in air. This photo shows a magnesium ribbon burns brightly in air to form a white solid called magnesium oxide. This chemical equation represents the reaction occurs between magnesium and oxygen. Magnesium reacts with oxygen to produce magnesium oxide. We can study this equation in terms of redox reaction. The oxidation number of magnesium is 0 before it reacts with oxygen. The oxidation number of magnesium in magnesium oxide is positive 2. Hence, magnesium is oxidized because the oxidation number of magnesium increases from 0 to positive 2. On the other hand, the oxidation number of oxygen before it reacts with magnesium is 0. The oxidation number of oxygen in magnesium oxide is negative 2. So we can say oxygen has been reduced because the oxidation number of oxygen decreases from 0 to negative 2. So burning of magnesium in oxygen is an example of redox reaction because oxidation and reduction occur simultaneously or at the same time. Different metals have different reactivity with oxygen. Reactive metal will burn rapidly and vigorously in oxygen. A less reactive metal will react slowly with oxygen. We can compare the reactivity of metal with oxygen by observing the flame or the glow produced when the metal is heated in oxygen. The brighter the burning flame, the higher the reactivity of metal with oxygen. This diagram shows the setup of apparatus we use in the lab activity to investigate the reactivity of metal with oxygen. About 2 spatula of metal powder are placed on a piece of asbestos paper. Asbestos paper is a good heat insulator. It can help to save the combustion tube from cracking due to the thermal shock because the burning of metal in oxygen is a highly exothermic reaction. The glass wool placed in between potassium manganate 7 crystal and metal powder to prevent the metal powder from potassium manganate 7 crystal from mixing. The potassium manganate 7 crystal will decompose by heat and producing oxygen gas for the reaction. Metal powder is heated first using a Bunsen burner. When the metal powder turning red, it means it is ready to react with oxygen. Then we start to heat the potassium manganate 7 crystal. The oxygen gas released during the decomposition of potassium manganate 7 crystal will flow through the glass wool and start to react with the hot metal powder to form the metal oxide. You can click the link provided here to watch a video of demonstration for the reaction between different metals with oxygen.
Which of the metals shown is most reactive and which is least reactive? Can we compare the reactivity of magnesium and aluminium? To find out whether aluminium or magnesium is more reactive, we check out the reactivity of the two metals with dilute hydrochloric acid. Let us find out how to include other metals in this reactivity series.
Let's do a lab activity to compare the reactivity of metals with oxygen series of metals. This arrangement is called the reactivity series. Compare your constructed reactivity series with the electrochemical series that you have learned in Form 4. Where in the reactivity series would you place tin, mercury, silver, and gold? The reactivity series of metals is an arrangement of metals in the order of their reactivity towards oxygen.
You have learned that metals react with oxygen to form metal oxides. Do you think non-metals like carbon and hydrogen can react with oxygen too?
Let's try out this experiment. The idea is to find out the ability of carbon to remove oxygen from a metal oxide. Mix a spatula of each metal oxide to carbon in the crucible. Based on the observation, determine the position of carbon in the reactivity series. Aluminium occupies the position above carbon in the reactivity series. Therefore, there is no reaction between aluminium and carbon. Zinc occupies the position below carbon in the reactivity series. Therefore, zinc is less reactive than carbon. Zinc is reduced from zinc oxide to zinc. Carbon reduces all the metal oxides that are below itself in the reactivity series. It does not react with the metal oxides above it. Now that you know that carbon is placed between aluminium and zinc in the reactivity series, let's look at the position of hydrogen. Based on the observation, Determine the position of hydrogen in the reactivity series. Now, based on the observation, answer the questions given. Lead occupies the position above hydrogen in the reactivity series. Therefore, hydrogen is released when lead is reacted with hydrochloric acid. Copper occupies the position below hydrogen in the reactivity series. Therefore, hydrogen is not released when copper is reacted with hydrochloric acid. Hydrogen is released when all the metals above it is reacted with acids. Hydrogen is not released when all the metals below it is reacted with acids. Why do we need to know the position of carbon in the reactivity series? Carbon can be used to extract certain metals from their ores depending on its position in the reactivity series. Why do we need to know the position of hydrogen in the reactivity series? We can predict the possibility of displacement of hydrogen from water or acid relative to hydrogen's position in the series. The reactivity series of metals is a list of metals arranged in order of their reactivity with oxygen. The metal at the top of the list is most reactive.
In this lesson, you have learned that the reactivity of metals can be compared and arranged by reacting the metals with water, dilute acid, oxygen. The metals that can be arranged according to their reactivity. This is known as the reactivity series. We can use the electrochemical series to place some of the metals in the reactivity series. Carbon does not react with aluminium, so carbon is situated below aluminium. Carbon reacts with zinc, so carbon is situated above zinc. Therefore, carbon is positioned between aluminium and zinc. Hydrogen is below lead, and hydrogen gas is released when lead is reacted with acid. Hydrogen is above copper, and copper does not react with acid.
These are the 5 different metal powder that we use in the blackboard demonstration in the video clip just now. We have aluminium, zinc, iron, lead, and copper. Each metal powder will react with oxygen at different vigorosity. So we can arrange them orderly from the most reactive metal to the least reactive metal based on the brightness of the flame observed. We look at aluminium. Aluminium burns very brightly in oxygen. How about zinc? Zinc burns brightly with oxygen. So you will notice that the brightness of the flame produced when aluminium reacts with oxygen is brighter than the reaction between zinc and oxygen. So this indicates that aluminium is more reactive than zinc. So aluminium should place higher than zinc in the reactivity series of metal with oxygen. How about iron? Iron glows very brightly with oxygen. Lead also glows brightly, but when compared with iron, you can see the glow of lead in oxygen is slightly dimmer compared to iron. So lead is slightly less reactive compared to iron. And lastly, copper glows faintly with oxygen. So now we can arrange this metal from the most reactive to the least reactive metal. Aluminium is the most reactive metal among these five, followed by zinc, iron, lead, and the least reactive metal is copper. Reactivity series of metal with oxygen. The reactivity series is a list of metals arranged according to their reactivity with oxygen. This is the reactivity series of metal with oxygen. On top of the list is potassium, because potassium is the most reactive metal when react with oxygen, followed by sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, copper, mercury, silver, and aluminum. So the reactivity of metal towards oxygen decrease going down the series. Now let us refresh back the observation that are recorded in the blackboard demonstration in the video clip just now. We had chosen aluminum, copper, iron, lead, and zinc in the demonstration. Aluminum powder burns very rapidly with bright flame. A white powder is formed. The color of aluminum metal is gray, and then the residue or the product formed during the reaction is white powder. The white powder form is called aluminum oxide. Aluminum powder burns very rapidly, so the brightness of the flame produced indicate the reactivity between aluminum and oxygen is very high. Now we look at copper. The color of copper metal is brown, as you can see in the picture. The residue of the reaction or the product formed from the reaction between copper and oxygen is black color. The color of the product remains black in hot or cold. This black residue is copper 2 oxide. It's the metal oxide of copper. The copper powder glow faintly, indicate the reaction between the copper and oxygen is not very reactive. How about iron? Iron powder glow very brightly, and then reddish brown powder is formed. The initial color of iron metal is gray solid. The end product of the reaction is iron 3 oxide. Iron 3 oxide is the iron rust that you learned in the previous lesson. The color of the rust is reddish brown. And then lead. Okay, we look at the color. Initial color of lead is the dark gray solid. At the end of the experiment, the color of lead 2 oxide is brown when hot and yellow when cold. Lead 2 oxide changing color from brown to yellow when cooled and reverting to brown when heated. We call lead 2 oxide is a thermochromic metal oxide because it is able to change color due to a change in temperature. This is the color of zinc oxide. Zinc oxide is another thermochromic metal oxide. Zinc oxide is able to change its color. It is yellow when hot and white when cold. So zinc powder burns quickly with bright flame. Yellow powder is formed when hot and white when cold. Please remember that lead 2 oxide and zinc oxide are two thermochromic metal oxide that is very popular in your exam question. So you need to memorize the color of these two thermochromic metal oxide. Reactivity series. Carbon and hydrogen also react with oxygen to form covalent compound. For example, carbon reacts with oxygen to form carbon monoxide or carbon dioxide. Hydrogen also reacts with oxygen to form water. That is why we can include carbon and hydrogen into the reactivity series. So how the position of carbon is determined? We can determine the position of carbon inside the series, reactivity series, by heating charcoal with oxide of another metal. Charcoal is carbon. So the theory applied here is, if the carbon powder is able to displace another metal from its metal oxide, that means carbon is more reactive than that particular metal, and carbon is placed above that metal. In this experiment, we only choose two different metal oxide, aluminium oxide and zinc oxide. As you can see here, we mix the carbon or charcoal with aluminum oxide in a crucible and place on a pipe clay triangle, and then we heat it strongly. As you can see here, the observation recorded no visible changes when carbon is heated with aluminum oxide. So before the experiment, aluminum oxide is white powder. After the reaction, also white powder. So that means no reaction occurred. So carbon cannot displace aluminum from aluminum oxide. That means carbon is less reactive than aluminum. So carbon is placed below aluminum in the reactivity series. After that, we try to heat the mixture of carbon and zinc oxide. The photo here shows the observation when zinc oxide is heated with carbon. As you can see here, there is a black powder. Black powder is carbon or charcoal. The yellow powder here is zinc oxide. When we heat the mixture, the temperature rise, the white zinc oxide turns into yellow. So zinc oxide and charcoal powder, the mixture glow brightly. At the end of the experiment, a gray solid is formed. The gray solid is zinc powder. So that means at the end of the experiment, we can collect gray solid. That means we obtain zinc powder from this chemical reaction. So carbon had displaced zinc from zinc oxide. So this indicates that carbon is more reactive than zinc. So carbon can displace zinc from zinc oxide. So the position of carbon inside the series is placed above zinc. Okay, this chemical equation shows the reaction that occurred when mixture of zinc oxide and carbon are heated. Zinc oxide react with carbon, and then the oxygen here is taken away by carbon to form carbon dioxide. So carbon displaces zinc from zinc oxide. So carbon is more reactive than zinc. Carbon is placed above zinc. So where is the position of carbon? Here. Okay, carbon is placed between aluminum and zinc in the reactivity series of metal. Now let's see how to find out the position of hydrogen in the reactivity series. The diagram here shows the setup of apparatus that can be used to determine the position of hydrogen in the reactivity series. We choose zinc oxide and iron 2 oxide to react with hydrogen gas in this experiment. So we place zinc oxide powder on an asbestos paper inside a combustion tube, and then we heat the metal oxide first. At the same time, we add sulfuric acid into a round bottom flask that containing zinc granule. We add hydrochloric acid into the round bottom flask through this tester funnel, and then the end of the tester funnel should be below the level of sulfuric acid. This is to make sure that the hydrogen gas produced from the reaction between sulfuric acid and zinc powder has only one exit, that is the delivery tube. So we can make sure the hydrogen gas produced is channeled into the U-tube, into a U-tube that containing anhydrous calcium chloride. This anhydrous calcium chloride is used to dry the hydrogen gas. We need anhydrous calcium chloride to absorb the water, the moisture produced. So this can make sure that only hydrogen gas will enter the combustion tube and reacts with zinc oxide or iron 3 oxide. The flame of the excess hydrogen gas here, we need to burn the excess hydrogen gas to prevent explosion. So by passing the dry hydrogen gas over the hot metal oxide, if the reaction occurred, that means hydrogen is able to displace metal from the metal oxide. This indicates the hydrogen is more reactive than the particular metal. So let's see. When we pass through the hydrogen gas over the hot zinc oxide, no visible changes occur. So we know hydrogen is less reactive than zinc. Again, we try with iron 3 oxide. When we pass the dry hydrogen gas over the hot iron 3 oxide, the reaction occurs. The initial color of iron 3 oxide is brown solid. After the experiment, we obtain gray solid and water vapor. So you can see some water vapor collected at the end of the combustion tube here. You will see the water vapor collected here. So from this observation, we know hydrogen is more reactive than iron. So hydrogen can displace iron from iron 3 oxide. We can also study this equation or this reaction in terms of redox reaction. The oxidation number of hydrogen is 0. The oxidation number of hydrogen inside water molecule or at the end of the experiment is positive 1. So there is an increases of oxidation number. So we say hydrogen had undergo oxidation. On the other hand, the oxidation number of iron changed from positive 2 to 0. So iron had undergo reduction. You know, this is an example of redox reaction. And the position of, now we can arrange the position of hydrogen in the reactivity series of metal. Please take note, there's no wording with oxygen at the back, because this reaction does not involve oxygen gas. So the reactivity series of metal, the hydrogen is placed between zinc and iron. Now let's look at the summaries. Reactivity series of metal. We can arrange the series of metals in according to their reactivity. On top of the list is the metal reaction. Is a chemical reaction that oxidation and reduction occur simultaneously, or you can use a word occur at the same time to replace the word simultaneously. Question A2. Write the chemical equation for the reactions in set 1. So in set 1 we heat carbon and iron 3 oxide, and then reaction occurs. So the oxidation number of ions in iron 3 oxide is positive 3. The oxidation number of ions in iron metal is 0. Reaction occurs in set 2 but no in set 3. Carbon displaces copper from copper to oxide. The explanation: carbon is more reactive than copper. And for set 3, carbon cannot displace magnesium from magnesium oxide because carbon is less reactive than magnesium. C1. Now arrange X, carbon, magnesium and iron in descending order of reactivity. Descending order means from most reactive metal, starting with from most reactive metal to the least reactive metal. So this is the arrangement of metal in descending order. Magnesium is the most reactive metal, followed by carbon, iron, X, metal X and copper. Suggest metal X. Metal X is a metal that's located in between iron and copper. So it should be lead. D. Draw a label diagram for the apparatus setup used in set 2. So you need to draw a label diagram like this. You have crucible, you need to label crucible, you need to label pipe clay triangle, and then the reactants that we use in set 2 is oxide of X, and then we identify X is copper, so label copper to oxide added with carbon, and then tripod stand, and then remember to label heat with an arrow. Now let us look at this question. Question 8, SPN 2016. Let's refer to this diagram. Iron ore, iron 3 oxide mixed with limestone. Limestone is calcium carbonate, and coke is carbon in a blast furnace. And then under high heat, the iron ore start to react with carbon. After the chemical reaction, we can collect the molten iron at the bottom, at the outlet at the bottom of the blast furnace. That means carbon is able to displace iron from iron 3 oxide. Let's look at question B. Based on the situation 2, the production of iron in industry through the reaction between iron ore, you refer to iron 3 oxide, and coke, refer to carbon, is shown in the chemical equation below. iron 2 oxide, iron 3 oxide react with carbon, we get iron, pure iron, and carbon dioxide. So if the factory is able to process 480 kg of iron ore a day by using excess carbon, calculate the mass of the iron produced. First, step 1, you need to find out the number of mole of ions contained in 480 kg of iron ore. So we need to convert the unit of iron, the mass of iron, from kilogram to gram. So 480 kg is equal to 480,000 grams of iron. So divided by the relative formula mass of iron 3 oxide, then you can find out the number of mole is equal to 3,000 mole. So we have 3,000 mole of iron ore in the blast furnace. So how many mole of iron, pure iron, molten iron that I may obtain? So based on this chemical equation, 2 mole of iron 3 oxide will produce 4 mole of iron. So if I had 3,000 mole of iron 3 oxide, I may collect 6,000 mole of pure molten iron at the end of the chemical reaction. So 6,000 mole of iron, pure molten iron, is equal to how many kilogram? So the mass of iron produced is equal to 6,000 times 56. 56 is the relative atomic mass of iron. So I may obtain 336,000 grams equal to 336 kilograms of molten iron. Now let us move on to question 2. Determine the oxidation number of iron in compound Fe2O3. The first part of this question, the oxidation number of iron is positive 3. And state the IUPAC nomenclature of the compound. What is the correct naming for Fe2O3? It is iron 3 oxide. The oxidation number is written in Roman numerical number in bracket. Now we move on to question 8, 2013. The following are the formulae of two compounds, Mg2 plus and Fe2O3. Based on the formulae, state the oxidation number of magnesium and iron, and then you need to name the compound using IUPAC nomenclature. What is the oxidation number of magnesium in magnesium chloride? You can answer this question in table form. The oxidation number of magnesium is positive 2. And the oxidation number of iron in Fe2O3 is positive 3. The correct naming of magnesium MgCl2 is magnesium chloride. And the correct naming for Fe2O3 is iron 3 oxide. You may ask why we need to include a Roman number in bracket for iron 3 oxide but no in magnesium chloride. If you still remember the transition element that you learned in chapter 4, from 4, transition element can exhibit or show different oxidation number. That is one of the special characteristics of transition element. So iron can have oxidation number, for example Fe2 plus, the oxidation number is positive 2. Fe3 plus ion, the oxidation number is positive 3. So iron may show different oxidation number. It can have positive 2 or positive 3, depend on the charges on the ions. So we need to include a Roman number in a bracket to indicate the oxidation number of ions in this compound. But magnesium is not a transition element, so magnesium can have only one oxidation number, as Mg2+. That is why we don't include a bracket with Roman numerical number in the naming of magnesium chloride. Question B. Diagram H shows the apparatus set out for an experiment to determine the order of metal X, metal Y, magnesium, and metal Z in the reactivity series of metal toward oxygen. So look at diagram N. We have metal Z here, metal Y, and magnesium in this combustion tube. And potassium manganate 7 is heated to release. The residue is zinc oxide. So we can replace metal Z and Y with its name. So magnesium is the most reactive metal among these three, followed by Z. Z is zinc, and Y is copper. Question 1. State the type of reaction occurs when oxygen reacts with the metal. We take example from set 1. Copper react with oxygen. It forms copper 2 oxide. Set 2. Magnesium react with oxygen. It forms magnesium oxide. And zinc react with oxygen. It forms zinc oxide. So this is a reduction. So we can see oxidation and reduction occur simultaneously. So you can put down your answer, redox reaction. Question B. Based on observation in table 8.1, identify metal Y, metal Z, and arrange metal Y, metal Z, and magnesium in descending order based on their reactivity. So metal Y is copper, Z is zinc. So if we arrange in descending order, it means from the most reactive metal to the least reactive metal. So starting with magnesium, followed by zinc and copper. Lastly, you need to write the chemical equation as required by the question for the reaction between metal, magnesium, and oxygen. So this is the chemical reaction for the reaction between magnesium and oxygen. Question 10, SPM 2015. Diagram 10 shows the apparatus set out of an experiment to study the redox reaction between hydrogen gas with different metal oxide. So in this diagram, you can see oxide of X, unknown oxide X, Y, and Z. And then we pass through the dry hydrogen gas through the hot metal oxide. Let's refer to the table 10. When hydrogen gas is passed through metal oxide X, yellow powder glow brightly and change to gray solid. Glow brightly indicates the chemical reaction occurred between hydrogen gas and oxide of metal X. So that means hydrogen gas had displaced metal X from its oxide. That means it also means hydrogen is more reactive than metal X. If we arrange metal X and hydrogen in the reactivity series, the position of hydrogen gas should be above or higher than metal X. Then we move on to this reactivity series. So hydrogen is placed at the middle of the reactivity series, and then metal Z is magnesium. Question B. Arrange metal X, Y, Z and hydrogen. So we need to include hydrogen in this reactivity series in ascending order. So from the least reactive to the most reactive. So you start with copper because copper is the least reactive metal among these three, followed by lead, hydrogen and magnesium, and the reactivity increases from copper to magnesium. Number 3, by using one of the reactions occurred, explain the meaning of redox reaction. So let's say we take the example of lead 2 oxide react with hydrogen. Hydrogen gas displaces lead from lead 2 oxide because hydrogen is more reactive than lead. So we study the oxidation number of hydrogen. Before the experiment is 0, at the end is positive 1. So this is an oxidation process reaction. Oxidation number of lead is positive 2 before the experiment, at the end is 0. So oxidation number of lead decreased from positive 2 to 0. So you can answer like this. Lead 2 oxide is reduced because the oxidation number of lead decreased from positive 2 to 0. And hydrogen is oxidized because the oxidation number of hydrogen increased from 0 to positive 1. So oxidation and reduction occur at the same time. So this is a redox reaction. Lastly, I would like to thank you for spending your time to watch this video.